Let's get started here with the rotational kinematics problem. For this one, we have a globe that's initially at rest, and it's going to begin to speed up and start spinning, and we first want to get the angular acceleration of the globe. So we know it's initially at rest, so our initial velocity is 0. We're told that it rotates through an angle of theta, so that's our delta theta, and our time then is just going to be t. So we can use our delta theta equation here. We know that initial velocity is 0, so that whole term goes away. And so we just get theta equals 1/2 alpha t squared. And when we solve for our angular acceleration, we're going to get that it's going to be equal to 2 theta over t squared. Moving on to part B here, we want to think about the tangential acceleration for a point on the equator of the globe. So the globe is accelerating angularly like that, and we want to think about the tangential acceleration of that point right there. And so we know the link there between tangential acceleration and angular acceleration is just a equals r alpha. So that means that our tangential acceleration here is just going to be our radius times 2 theta over t squared. And if we simplify that, we get that our tangential acceleration is just 2r theta over t squared. Alright, for this next one, we have a car that starts from rest and accelerates at a constant rate. And we know that it accelerates to a velocity of v, and the wheels rotate through an angle of theta. So this is one where we have a mix of both angular quantities and linear, in this case translational quantities. So let's go ahead and set up all the things we know. I have both charts set up, so we know we're starting from rest, which means both initial velocities are 0. We're ending at a linear velocity, or translational velocity of v, and we undergo an angular displacement, the wheels do at least, of theta during this time. So we have two options, okay? We can either say that this final velocity, okay, is going to be equal to v over r, and that just comes from the fact that v equals r omega, or we could say that our linear displacement is just going to be equal to r theta, and that comes from the fact that delta x equals r delta theta. Either one will work. I'm ultimately going to use my linear quantities though, because I'm looking for my linear acceleration, so I'm just going to go ahead and stick with those. But you obviously could find your angular acceleration and then convert. So we have v squared equals 0 squared plus 2 times a times r theta, and that means that when we solve for our acceleration, we get that our acceleration is going to be v squared over 2r theta. And we would have gotten the same answer if we had done everything with angular stuff. So for the second part, I'm worried about how the angular displacement would change if a few different things happen to the car itself. The first is the car accelerates to 3 times its original speed. So here I'm really just concerned about my angular quantities, so I'm going to focus on that. And I'm worried about the original situation and the new, so I'm going to have two setups here. So I know my displacement originally was delta theta, and I started from rest. And I'm just going to say my final angular speed was omega, and my angular acceleration was alpha. I could substitute in some of the things I have over here for them, but they're just going to cancel out in the end. My new situation, I'm going to have theta prime. I'm still starting from rest. I'm accelerating to 3 times the speed. So if my linear speed is 3 times as much, so is my angular, and that just goes back to this relationship that I have back here. And it's the same angular acceleration alpha. So I can go ahead and set up two equations here. In both cases, I'm going to be doing omega final squared equals omega initial squared plus 2 alpha delta theta. And so we have just omega squared, that term is 0, is equal to 2 alpha theta. And if I solve for theta, I get omega squared over 2 alpha. And now I'm going to go ahead and do the same thing for theta prime, except my final speed now is going to be 3 omega. So 3 omega squared equals 0 squared plus 2 alpha times theta prime, using this same equation here. And so I end up getting 9 omega squared equals 2 alpha times theta prime. And when I solve for theta prime, I get that it's 9 omega squared over 2 alpha. This one is one where it's pretty easy to see the difference. The difference is just that 9 there. So that means that omega prime, my new angular displacement, is going to be 9 times my original angular displacement. For the second part, we're concerned with the case where the wheels on the car had a radius that was twice as big and still accelerated to a speed of v. So in this case, what I'm going to think about is if the car is accelerating to the speed of v with the same linear acceleration, that means it's going to have the same delta x in both cases. So I'm going to set up my original and new here as well, but I'm going to use this as my link. So I can say that delta theta times r is going to be equal to delta x. So originally, it's just r theta is what was equal to my delta x. My new situation, I now have twice the radius, so 2r theta equals delta x. And now this is my theta prime, that new angular displacement. Those two are equal to each other, so I can just set them equal. So I can say r theta equals 2r theta prime. Those r values cancel out, and what I'm left with is that my new theta is equal to my original theta over 2, so half as much, which makes sense because the wheels will only have to rotate half as many times if they have twice the radius and therefore twice the circumference in order to travel that distance. So for this next one, we have a conceptual question about riding on a carousel and why it's a little bit more thrilling to ride on the outside than on the inside. So if we think about a carousel that's rotating at some angular speed, and we consider two objects or 2 points on the carousel, one a little bit closer to the center here, one a little bit further away. Both points are going to have the same rotational speed, okay, because they're rotating with the carousel. However, if we think about their tangential velocity, okay, so the tangential velocity of the inner one and the tangential velocity of the outer one, keeping in mind that that tangential velocity is equal to r omega, when we increase the radius like we have for the outer one, that increases the tangential velocity, and therefore their tangential velocity is faster if you're on the outside. Alright, so we move on to this conceptual one here, and we have 3 coins sitting on a record. Our platform is rotated at a constant rate, sitting various distances from the center here, as you can see. And the first thing we want to do is rank them from least to greatest in terms of their angular velocity. Well, since they're all sitting on the record, they're all going to be rotating at whatever rate the record is rotating at. So that means that the angular speed of A equals the angular speed of B, which is equal to the angular speed of object C. For the next one, we want to rank their tangential velocities here, and we keep in mind that tangential velocity is going to be equal to r times the angular velocity. Since they all have the same angular velocity, what we're really going to care about is the radius, and so the one that's furthest away is going to have the greatest tangential velocity, and the one that's closest is going to have the least. So we can say the tangential velocity of A is going to be less than the tangential velocity of B, which is less than the tangential velocity of C. For the last one here, we want to rank their centripetal accelerations. So we have 2 ways of finding that. We can do v squared over r, but that's going to be a little bit tricky because they all have different tangential velocities and different radii. So instead, I'm going to use the fact that centripetal acceleration is omega squared r, and then I know that the omegas are the same for all of them. They all have the same angular speed, and I can just focus on radius. So the one with the greatest radius is going to have the greatest centripetal acceleration. So the acceleration of A is less than the acceleration of B, which is less than the acceleration of C, the same ranking as for tangential velocity. So we have a motion graph 1 here, and the first question is during what interval or intervals is the object slowing down. So what we're going to be thinking about is we're looking for situations when it's approaching the x-axis, so that would be right in here, which means it's slowing down from 3 seconds to 5 seconds until it crosses the axis at this point here. And then it's also slowing down, as we can see, from 6 seconds until 8 seconds as it's approaching the axis there as well. Question B asks about the overall angular displacement of the object, and so really what we're doing is we're comparing this area here above the x-axis, that trapezoid, to this area here below the x-axis, which is negative, that triangle, and we can see that the area above the x-axis is greater, which means overall this is going to have a positive angular displacement. Question C here asks during what time interval is the object rotating at a constant angular speed? So we're looking for situations when our slope is equal to 0 because our slope represents our angular acceleration. So if slope is 0, then our angular acceleration is also 0. And we see that that occurs here from 0 seconds to 3 seconds. We have a slope there where it's just a constant angular velocity. You also could make the argument, I guess, from 8 seconds to 10 seconds, but that would also be an angular velocity of 0. So to say it's rotating at an angular speed kind of implies that it's moving, and that would be a case from 8 seconds to 10 seconds where it's not moving at all. D asks when the object reaches its maximum angular displacement relative to its starting position. So we can see here, and we have the areas filled in, that it has a positive angular displacement from 0 seconds all the way to 5. It then turns around, changes direction, and undergoes some negative angular displacement, but not enough to go back to 0 or even go back past 0 and go a greater distance than the negative. So that means that at this point here, when it turns around and starts heading back to where it started, just like a regular position versus time graph, it's going to reach its maximum angular displacement. So it's going to be at 5 seconds. The last part asks us to draw a graph, so I'm going to zoom in here on the graph, and I'm going to go ahead and label this x-axis with the times that correspond with my velocity versus time graph. And so now I'm going to think about the motion of this object. So I see this first part up to here. We have a constant angular speed from 0 seconds to 3 seconds. So my line is going to be a straight line with a positive slope up to 3 seconds. I then, from 3 seconds to 5 seconds, slow down to a stop. So I'm going to start seeing some curvature here to my graph, showing that I'm slowing down to a stop, decreasing my velocity. Then from 5 seconds to 6 seconds, it speeds up in the negative direction. So we're going to speed up a little bit here in the negative direction. And then from 6 to 8, we slow down once again to a stop while still traveling in the negative. This last little bit from 8 to 10, that's just showing the object not moving. So that's just going to be a horizontal line. And we can see here, based off of our graph, that right there at 5 seconds, we clearly are the furthest away from our starting position, which matches our answer from D.